Hello students, welcome back to next session. In earlier session we have seen condensers as well as compressors, types of compressors and types of condensers. In this session we will see the third component, evaporators, types of evaporators. So all these topics we have seen. Now we are discussing the evaporators. In next session we will be completing the expansion devices where we are completing the entire unit. So evaporators are heat exchangers. So in condensers are also normally acts like heat exchangers, whereas evaporators also heat exchangers where a refrigerant is evaporated at low temperature and pressure. So this is the difference between evaporator and condenser. So here it happens and the refrigerant is evaporated at low temperature and pressure. The primary function is to remove heat from the refrigerated space or material. So to remove the heat from refrigerated space or material, the evaporator is crucial component in the refrigeration system, that is transferring heat from the product medium or space to be cooled to the refrigerant. In common terminology, the word evaporator may also refer to all coolers, even in systems where no evaporation takes place. The system using secondary refrigerant. The refrigerant absorbs latent heat from the load and exits the evaporator as a dry gas. So that is the refrigerant heat transfer is taking place. So types of evaporators, there are dry expansion DX evaporators. In these evaporators, the refrigerant is metered such that it extremely evaporates before leaving the evaporator. So the vapor leaving the evaporator is slightly superheated to prevent liquid refrigerant from reaching the compressor. So refrigerant supply to the evaporator is controlled by a thermostatic expansion valve. So the key characteristics of DX evaporator is this moderate superheating of vapor drawn off and simple in operation, limited thermal efficiency in sections where the refrigerant is in the vapor phase, used primarily in the moderate capacity machines, requires more surface area compared to equivalent flooded type evaporators. So subtypes of DX cooling DX evaporators are DX cooling coils used for cooling air, DX chillers used for cooling water or other liquids. So here this is the DX evaporator. So this is the liquid in and liquid, that is vapor is coming out, and this is the expansion valve. So this is the thermostatic expansion valve. So evaporator is also like condenser, and where we have coil, evaporator coil here, and this is the DX cooling coil, and we have chillers also. So next one is flooded evaporators. These evaporators are only evaporate a part of the refrigerant volume that is delivered. The outlet of these evaporators requires a liquid separator or surge drum, which contains only vapor at the top, while unevaporated liquid is fed back to the evaporator inlet. So these evaporators have high heat exchange efficiency since the entire internal surface is in contact with the liquid refrigerant. So they provide rapid cooling but tend to be bulkier and require a large refrigerant charge. So key characteristics of flooded type are high efficiency due to complete refrigerant contact with the heat exchange surface and requires a large refrigerant charge and uses a low side float valves to maintain a constant liquid volume in the separator. A float valve regulates refrigerant expansion and maintains a liquid pool of refrigerant inside the evaporator. So this is the schematic of flooded type evaporator. So the liquid refrigerant is sent here, and that comes out as a vapor. So this is the arrangement of the evaporator, and this is flooded type. Instead of having coil, so we are using the flood type. So flood of refrigerant. So this is another simple arrangement of evaporator. So evaporator classification by shape, tubular evaporators can be bare pipe or it is a finned type also, used in air conditioning and refrigeration systems, and plate type of evaporators, so constructed with hollow passages in a flat plate for refrigerant flow, and evaporator classification by refrigerant circulation method, and gravity circulation evaporators, forced circulation evaporators. It uses a pump. External device is required for forced circulation, so a pump is used here. So air cooling evaporators have finned pipe coils. In small coolers, fans blow air over the coil, so fans are also used. Common materials are aluminum fins and copper tubing, so hollow carbons, and stainless steel or aluminum tubes for ammonium based systems. And proper tube sizing promotes boiling turbulence, enhancing heat transfer. Fin spacing is an important design factor. Closest spacing, so that results in compact unit, and wider spacing, large unit, but allows more frost accumulation before defrosting. So evaporator liquid cooling evaporators. So typically shell and tube or shell and coil type, and DX expansion circuits have refrigerant inside the tubes, ensuring suitable continuous velocity. So baffles improve water inside the turbulence. So baffles also can be used to improve the water side turbulence. And flooded shell and tube evaporators are common in water chilling applications. So that is air conditioning and water flow inside the tubes. So which the while the refrigerant chills in from the outside, and low side float valves regulates refrigerant flow and are designed to operate at temperatures between 4 to 9 Celsius. So water flow considerations, water velocity in evaporator systems typically ranges from 1 meter per second to 3 meters per second. The flow must be kept constant to prevent freezing of water inside the tubes. So the recommended practical water temperature for air conditioning applications, so around 6.5 degrees Celsius, never lower than 5 degrees Celsius. So here the plate type evaporators. Plate type evaporators are formed by sheet metal cladding and tubular coil. The major application of flat plate evaporators is cooling solid products via conduction. So the extended flat face can be used for air cooling, liquid cooling if immersed in a tank. Applications are limited use in air cooling systems, preferable when heat transfer requirements are low. Frosting can be concerned in finned tube evaporators, making plate evaporators a better alternative. So material considerations here, evaporator materials can be compatible with the refrigerant and the surrounding environment. So for example, copper must not be used with ammonia. So a special consideration are needed for marine environments due to corrosion risks. So defrosting, so frost formation in evaporation. So this is another drawback. Defrosting should be necessary. Defrosting should be done, and formation is obvious in all evaporators. When an evaporator operates below 0 degree Celsius, frost gradually accumulates on the heat exchanger surface due to moisture condensation. So, even in the freezer box, we can see in our refrigerator, domestic refrigerator, there normally the frosting taking place because it goes always lesser than the 0 degree Celsius, and frost accumulation issues acts as an insulation. Thick layers of frost reduce the heat transfer capability. Airflow obstruction in forced convection coils, frost reduces the airflow rate, and defrosting methods are common methods. Manual defrost method, shutdown method. So we have to shut down it, we have to off it so that the defrost can be taken place. Time shutdown defrost method, electric defrosting, water defrosting, hot gas bypass defrost system. So here manual defrost method, in the just we are switching off the refrigerator and keeping it for a while, so defrost will take place. So this system is shut down, allowing the temperature to rise, leading to natural defrosting, and results in a progressive increase in condenser temperature. And time shutdown defrost method. So system shutdown occurs at regular intervals to prevent excessive frost buildup. And electric defrosting utilizes built-in heater elements to melt the frost, and mostly used in smaller units but is expensive for larger ones. And water defrosting, water is anti-freezing solution, is periodically poured over the evaporator surface and which is drained, and limitations are not not convenient for continuous low temperature environments, so it is not much used and it is not suggestible also. Hot gas bypass defrost. So this is another method. And hot gas we can blow through the evaporator coil. Most commonly used method along with water defrost. And working principle is discharge gas. Flow the compressor is from the compressor is redirected to the evaporator. The evaporator temporarily functions as condenser, and the heat of condensation melts the frost, which is then drained away. So alternative methods are reverse cycle defrosting. So evaporator and condenser switch functions. So we can switch the functions of these two and we can get the defrost done, and mostly used in small refrigeration units. And this is the bypass, same like what we have seen in condenser, it is also same. So the evaporator is placed here and condenser is placed here, and bypass line is provided here. It is same as the condenser bypass. Evaporator design factors affecting heat transfer rate. The efficiency of an evaporator depends on the following: surface area, temperature gradient, quantity of cooling medium, condition of surface. Tube selection criteria is the following factors influence the choice of tubes of evaporators: cost, workability, exchangeability, expansion, contraction properties, resistance to corrosion, tube diameter. So these are the factors to be considered while selecting the tube. So design steps, designing an evaporator involves deciding on the evaporator temperature, so what temperature it handles, and selecting the refrigerant, evaluating the refrigerating effect. So key parameters are the temperature difference. So TD is the temperature difference, air entering the evaporator space temperature, and saturation temperature of the evaporator pressure. So typical values are 7 degrees to 10 degrees Celsius. The governing equation, as we have seen in the earlier session also, Q equal to UATD, where Q is the cooling capacity, U is the overall heat transfer coefficient, and A is the heat transfer area of heat transfer, TD is the temperature difference. So here the precise heat transfer calculation can be done. The same equation we have seen in the earlier session also. So Q equal to UA delta Tm, and this is the equation. After there is a derivation for this, but it is not required for our syllabus. So delta Tm is equal to T1 minus Tb minus T2 minus Tb, that is natural logarithmic of T1 minus Tb divided by T2 minus Tb, where Tb is the refrigerant boiling temperature, T1 and T2 are cooling liquid inlet and outlet temperatures. So pipe length calculation can be L equal to A by pi d, and where A is heat transfer area, D is tube diameter. So wall thickness can be calculated using this relation. So wall thickness, that is T equal to PD by 2F. So where P is the maximum pressure, D is tube diameter, and F is hoop stress. Hoop stress is also taken into consideration to calculate the thickness, wall thickness. So we will see one problem on this, a simple problem. A storage room maintained at minus 16 degrees Celsius has a cooling load of 7 kilowatt. Design an evaporator temperature is minus 25 degrees Celsius. Copper tube is having the length of diameter of 250 millimeter is specified for the evaporator coil. Determine the length of the evaporator pipe required to meet the cooling load. The U factor of 8.9. So U is also given 8.9 watts per meter square degree Celsius. It can be considered, and the solution is straightforward. So Q equal to UATD. So now A can be calculated by substituting these values. So we know that, right, we know A equal to Q by UTD. So UTD here, the U that is Q is given, that is 7 kilowatt. So that is watts, we are converting into watts. So 7000 divided by 8.9, U is 8.9, and we have 9. 9 is given, and equal to 87.39 meter square. So this is the area. Now we are calculating area first, and then L. So L can be determined. L can be calculated now using the length calculation that I have given you, and 87.39 divided by pi into. So we know the area. So with the area formula, we can calculate this pi into 0.250. So it comes 111 meters. So length is 111 meters. So now we have determined the length of the evaporator pipe required to meet the cooling load. So very simple problem and straightforward problem using those two formula that I have given you. You can easily calculate this, and remember these equations. That is enough, students. No need to learn the derivations. So we stop here, and we will see the expansion devices. That is the last topic we will see in next session. So these are the references. We can refer these books, and we stop here. Thank you, students.